going to deal with the springs in Unit 2. The springs, this is the spring having a length L and force F1 and F2 are there. The definition of the spring, what does it spring means? That the spring does not transmit any forces from one spring to another, or it never resists bending. Always it will be in high tension. This is the characteristics of or property of a spring. Now, if these springs are connected together and if you want to solve the displacement, how will you apply the finite element equations to the spring? And how will you find the reactional forces? That's what we are going to see in the spring problems. There are a spring assemblage. The spring are assembled in such a way with arbitrarily numbered. Arbitrarily numbered means it is not, there is no hard and fast rule for that. Arbitrarily it is numbered. Nodes 1 and 2 are fixed. In your node 1, 2 are fixed. And a force of 500 Newton is applied at the node 4. Node 4 or 500 Newton apply pandrom. And the spring constants for 3 springs are there. K1 is 100 kilonewton per meter. K2 is 200 kilonewton per meter. So K3 is kilonewton per meter. First we are going to this green ink indicates the elements and the blue ink indicates that node 1, 2, 3, 4 and 2. These two are fixed ends. Now I am going to take the element 1 and element 1 consists of 1 and 3 and I am going to apply finite element equations to find out the global stiffness matrix. The global stiffness matrix, though this is the finite element equation. This is the finite element of any spring element. Here F1, F2, if it is a nodes are F3 and 4, it will be 3 and 4. If it is 5 and 6, it will be 5 and 6. So according to that, nodes you apply the finite element equations of the spring. So I have selected, this is the first equation. This is the first equation and F1 and F3. Node 1, node 2 is at the extreme end, 1 and 2 are at the extreme ends. And after 1, next to the 1, that is 3. That is in the bar here. I'll show you that. So this is the element I have chosen 1 and 3. Second element is this one 3 and 4. Third element is this one 4 and 2. So according to for the first element F1 and F3, not F1 and F2. According to the element you just choose F1 and this is the finite element equation, general equation. So this F1 and F3 1 minus you string constants for the K1 that is 100 kilometer I have substituted and I have multiplied inside everything to find out the general equations of the finite element. So next I am going for element 2. Look at that U3 and U4. It is U3 and U4. I have returned this equation and again the K2 is 200 kilonewton per meter. So the 200 kilonewton per meter I am multiplying inside everything 200 and I am getting this equation. This equations I am getting it. So element 3 is 4 and 2. So 4 and 2 K3 element, that is K3 element, the element stiffness of the element 3. So this is the way I am getting it. Inga 300 put. This is 300 on the K3, the stiffness of the element 3. So I have, it is given. So this is what the equation. So now what is the procedure that I have to follow? I have to find out the assemblage element 1 equation, assemblage element 2 equation and 3 equations together to form a global stiffness matrix of the spring element. So this global stiffness matrix of the string element is, this is the one I got and I have just assembled it, then adding this 200, 300, this rearranging this and you got this. This is the stiffness matrix of that. Now we got this. Now what we have to apply? We have to find out the displacements. So apply the boundary conditions. Here the springs both are attached, both are fixed at the extreme ends. So in both two ends at the extreme ends, node 1 will be U1 is equal to 0, U2 is equal to, since it is fixed, node 1 is fixed, node 2 is fixed. So both will be 0. So the nodal forces, since neglected. This here the problem, it is not the self weight is neglected, all the forces becomes 0. F1, F2, F3, everything is becomes 0 except F4 because it is applied force that is given in the problem. So 500 Newton. So apply these boundary conditions here. I applied every boundary conditions here. Now that you want to find out the displacement. So U1 and U2 are 0. So cancel the first row and first column of the corresponding nodes. That is, this row completely goes and this row completely goes. So you remind this, only this you remind. So this is the remaining U3 and U4. Multiply this, 300 into U3 minus 200 into U4 is equal to 0. Minus 200 into U3, 500 into U4 is equal to 500. So on solving, this is the algebraic equation you can solve easily. Adding up this, multiplying, whatever it is, simplify it and you will get U4 is equal to 1.364, U3 is equal to 0.0. Now we are going to find out the reactional force. The reaction force at the extreme ends, in between that it should be 0. So extreme, the support reactions, we are support is fixed support. At the both the support, it should be, there should be a value which must be equivalent to the applied force. That reaction force which you are getting value should be applied equivalent to the applied force, so that we understood that system is in equilibrium. Now we have to find out the same thing, whatever I done before is followed. So R1, R2, R3, R4 reactions. This one, this is what I made it. U1, then I added it. Everything U1, U2, U3, 500 force, everything is force is substituted here, and U2 and U3 and U4 values are substituted here. You know U1 and U3 is 0, so that is U1 and U2 is 0, so everything is 0. So this is what I have done. Then I multiplied this 100 into 0, 0 into 0, minus 100 into 9.9091, 0 into 0.2. This all the things I have plused. Again 0 into 0, 300 into 0, 0 into 0.90, 3 into this one. So this is the way we have to multiply. You know the matrix multiplication. You do the matrix multiplication, you will get this answers and subtract that from the force. So now you got this, you subtract this minus this minus this minus this, I am getting this value. So R1 and R2 I am getting, see, R1 and R2, rest all becomes 0. So this R2 is the node, the fixed support, the last one, the last reactions at the last extreme end. So you are getting this value, So now we will verify that. So R1 plus R2 plus R3 is equivalent to this value should be added. If I add this, I am getting minus 500 kilonewton. Minus 5, this is what the applied force. So the reaction force is equivalent to applied force, but in the opposite sign. So what you have done is right. So write the results separately, which is what I have written here separately to show that your presentation is neat and clean. Thank you very much.